and equivalently this was done by Intel, and equivalently there was that 3D now by AMD. Now we will continue on this discussion on the evolution of instruction set architectures. So next step would be, as we know that an instruction basically has an opcode and operands. On the operand side, there are many decisions that need to be taken. For example, how many operands? Right? So what is the rationale behind having this many amount of operands? So this is one very important decision that we need to take, and the next is type of operands. And another important thing is there a relation between opcode and operands? Okay. So can I have, say, some instruction, there are some opcodes for which there are 2 operands, some opcodes for which there are 3 operands, and so on. If that is the case, and then these sets are quite large, like there are some, say, 30 different unrelated opcodes for which there will be 2 operands, and some 40 opcodes for which there are 3 operands, then what would happen here is, as I told you earlier, there are 2 levels of translation. First is your high level language gets compiled into a machine language, then this machine language is interpreted by your hardware. So every instruction has to be understood by your hardware, and that is what we call as decoding an instruction, right. So there are ones and zeros that are coming into your hardware, and the hardware should understand, yes, I have to do add on this, subtract on this. So there is an implicit understanding that is happening within the hardware, and when that is happening, the hardware should essentially realize what is the opcode and what are the operands, right. That is also a part of, your understanding process. Now if I can go and interpret my opcode and the operands concurrently, then my understanding process becomes faster, right. If I can go and interpret the operands independent of the opcode, right, let there be any opcode, my decoding or understanding of what the operands are independent of the opcode. If suppose such a scenario exists, then your understanding process becomes easy. I will be understanding, what do you mean by understanding? When we see the actual hardware, we will understand what do you mean by understanding. What do you mean by hardware understanding the instructions? But I can go and understand what the operands concurrently with, while I am trying to interpret what the opcode is. So instruction set architectures where the opcode is independent of the operands and vice versa are called orthogonal ISAs. Now we will try and be as orthogonal as possible. It's not possible to be completely orthogonal, but we will try and be as orthogonal as possible. Okay. So so if you look at the hack ISA that we did last semester, it is almost orthogonal, right. Now what is one necessary condition for an orthogonal ISA? What is one condition that will make orthogonal ISA possible?
Fixed length.
Fixed length. Okay. So I need to have fixed length. If I don't have fixed length, automatically it implies that depending on some opcode, some operand will be somewhere, etc. Okay. So mostly the RISC ISAs are more orthogonal than the CISC ISAs. Because RISC ISAs are fixed length when compared to CISC ISA. Okay. So, there are 3 points that we want to cover today. An instruction comprises opcode and operands. Now, we have to discuss more on the operands. Before that, for the implicit translation process, interpretation process, there are opcode, there are operands, and there should be an deciphering of the opcode and operands by the hardware, and that is going to be fast if you are going to have orthogonality established between them. And I will try to be as orthogonal as possible. I can't have that 100% orthogonality, and RISC ISAs are much more orthogonal than the CISC ISAs, right. That is why RISC processors do work faster. It is not that CISC does not work, but actually what happens is today if I have a CISC processor, the way the CISC processor is constructed, this is what we infer, nobody tells you how it is done, is that all the CISC instructions, there is a layer which interprets it and converts it into RISC. Every CISC instruction gets converted into a underlying RISC instruction, and then below this is a RISC processor which executes it. So, from the operating system or from the outside view, you only see a CISC processor, but the CISC instructions are not directly executed on a CISC processor by say CISC hardware. The underlying hardware is a RISC hardware, and all your CISC instructions are interpreted or converted into a set one or more RISC instructions, and it is executed on the RISC processor. This is how, so building CISC processors are becoming difficult, and this is how the complexity is basically taken care of. So, there is one hardware layer intermediately which will interpret the CISC and convert to RISC. So, this particular concept is called code morphing. Okay. So, there has been an extensive research in MIT. So, just Google this on code morphing. It is a very old concept, but it is a very interesting concept. Okay, now we will go on. The next discussion would be on the operands. So, how many operands? Should I have 2? Should I have 3? Right? These are all questions, right? And so, why should I have 3? Why should I have 2? So, what are the decisions? So, can you give me some reasons for why should I have 3 operands? Means like say add R1, R2, R3. Right? This is a 3 operand instruction. R1 is equal to R2 plus R3. So, what it will do? But I could have again add EAX comma EBX, where EAX is EAX plus EBX. Why should I have this? Why should I have this? What are the pros and cons of having a 3 operand versus a 2 operand?
If you want to preserve the original value, then you don't want to put the result back.
Okay. So, one thing is preserving original values. Right. So, this allows you to preserve original values, while this your one of the original value is lost. But normally registers are basically used as scratch pads. They only store temporary results. So, there is no reason so for example, normally I will have things like B equal to C plus or I will have B plus plus, where I have to update that value, or C plus plus, and C is equal to C plus A, right. So, normally when you look at many of the programming, when you see the actual code, you will see that a variable modifies itself as a part of your assignment statement, right. This is a normal thing that you see. So again, if you ask for an analytical proof, I can't give you, but this is how code is written. Okay. Very rarely you will say for example, somewhere like matrix multiplication, you will say A equal to B plus C, Aij is B. Very rarely you will see such type of constructs. So many point of time we will have a variable that is getting incremented or that is getting added to some other variable. So that is why we are happy with this scratch pads, where we are happy with 2 registers here. See, the point is when I say C equal to A plus B, both A and B are in memory. Okay, both A and B are in memory. So I have to fetch it from memory, right? I have to go and fetch it from memory and then add it. So my easiest thing is let A be stored at 1000, B be stored at 1004. I will go and bring into the thing is, I will if you use this, I will just say move into EAX 1000, and then I can say add EAX with 2004 and say let this be 1008. I will move 2008 EX. This is the easiest code I can write here, right? So even if you have instructions like this, these instructions are basically stored in memory, and I can go and access from there and store, right? Are you able to get this? But you could ask me, right, can I have something like even add 1008, 1000, 1004? This is the simplest instruction, but I will have 3 memory addresses here. So if I have a 3 operand instruction, can I do something like this? First and foremost, yes, if I have a 3 operand instruction and each operand can be a memory, then I can do this. But is it practically possible or not? What are the difficulties in this? I will write into the memory, read 1004 and 1000 from memory and then write the answer, add it and write back the answer into 1008. What will be the practical difficulty here?
Temporary registers. You need temporary some scratch pad to store value.
No, I can directly, you see, if you use the Intel architecture, you can directly access from memory as a part of your instruction. I could have something like this for sure, right? These 3 are valid instructions in Intel. Move EX, add EX and this. So what stops you from having such type of things? We may need more registers, but more practically what is the difficulty? Not only takes time. Now I am taking 3 instruction time here. It is impossible to implement this because for me to access memory, I have a memory management unit, and it can at a point of time take only one memory request from one CPU. Right? That's the practical difficulty. I could not have 2 memory requests, then the whole memory management unit, construction of that memory management unit becomes extremely complex. You able to get this? Right? So that is very, very important. So there is a difficulty in even creating this type of a memory management where I can go and read 2 simultaneously. I can give 2 address, read 2 address and also write 1, right. So and this should be viewed in the context of pipelining, which we will be talking next, okay. So there is a practical difficulty in having 2 memory operands in the same instruction, leave alone 3, even 2. So if you carefully look at the entire Intel ISA, that 1000 odd pages, 1000 plus pages, you will never find an instruction that has explicit 2 memory accesses, right. It will not have explicit 2 memory accesses, okay. There are some set of instructions we will see where both the destination and source are memory, but there are very, very specific instructions, right. But you will not find 2 fellows which are explicit memory access. So that is something that we need to basically keep in mind. So there are certain practical limitations which stop you from having now we are not even talking about 3 operands, we are basically saying that 2 operands itself I can't have both the operands as memory. Okay, right. Now, but why do, so some of the RISC architectures do have 3 address, right. So, what is the difficulty in having 3, other difficulty in having 3 addresses? And what are some things, right. So, what are some characteristics of RISC ISAs which enable you to have these 3 addresses? One thing is, so let us take some dig into compilers, has basically you take a C language construct. Now, this basically gets converted into what we call as 3 address code, or what we call as 3 address intermediate representation, IR, right, right. So, what is, so basically then this 3 address code is basically converted into a machine code, right. In our in the hack jack to hack conversion, your jack got converted into a 1 address code, correct, because it was push pop onto the stack, but push into something, pop into something, push from something, right. So, there was 1 address in many cases. So, but in general your C language or any high level language, the compiler will convert it into a 3 address code. That means an instruction with 3 operands, right, right. So, now if I have a 3 address, a 3 operand ISA, this translation actually becomes simpler. Okay. So, if I have a 3 operand ISA versus say this is a 2 operand ISA, certainly this is much easier than this. When you do the compiler course, you will also understand that generating a 3 address code is much simpler there, right. So, that is one motivation for a lot of a lot of ISAs to have 3 address operands. But when I look at 3 address operands, those type of ISAs fall into one category called load store ISAs. What do you mean by a load store ISA? There are only 2 instructions that touch memory, that access memory. So, in the entire computer science annals of computer science, access essentially means read or write, okay. That is one single word for read or write. Only 2 instructions in the RISC ISA, in the load store ISA access memory, one is called load, another is called store. Load will move from memory to a register, and store will move from register to memory. All other instructions operate on registers, like add, R1, R2, R3. These are all registers. So, I will not have a memory operand inside the add operation, okay. So, I will not have memory operands in any instruction except load and store. So, many of the ISAs today, the ISA inside your favorite ARM processor which is in your mobile phone are all 3 address ISAs, they are all RISC ISAs, they are all of fixed length, and they are all load store ISAs, because then the entire process becomes much more simplified. So, if you also carefully look at the hack ISA, it was also a load store ISA. There was a load and store instruction, there is an A instruction. So, if you go carefully and look back into your hack ISA which you did last semester, it is also a load store ISA. Okay. Now, next, so what are the type of operands that we could have? we have studied, we have been discussing on the number of operands. Now, what are the type of operands that we could have? We could have immediate operands, we could have register operands, and we could have memory operands. Immediate operand means in the instruction itself the value of the operand would be there. For example, suppose I have something like C equal to 0, this can translate to move ECX comma 0x0, this is hexadecimal representation, or C equal to 5, C equal to 10, then I can say move ECX comma 0xa, this is a hexadecimal value. Now, this is basically an immediate operand, and you will see lot of places where you are doing this initialization. So, this is an immediate operand, while this is called a register operand. Or we call it as a register addressing mode. So, these three are also called as addressing modes, the mode by which I address the operands. This is a register operand or register addressing mode, this is an immediate. The next one, so that is, so we have also seen some implicit addressing modes like your div that we talked last time, right. There are some registers that are hidden that are not explicitly stated in the instruction, but they get modified when you do a div instruction. So, we will talk about explicit, so we have already talked about implicit operands, we are now talking about explicit operands here. So, here ECX is a register operand and this is an immediate. So, whenever I see a variable and that variable is temporarily used, right. So, or I will start using register operations whenever I see a long expression a plus b plus k plus 2, then I will start using register operands here. Whenever I see a constant, I will use an immediate operand. So, these are all very simple things that we see. The more complex things come in memory. So, Intel has come out with excellent excellent thought process in terms of memory. Let us go and see the different memory operands. So, Intel could have base plus scale into index plus displacement, this can go up to 32-bit displacement. Okay. Base you can have all the general purpose registers, we call it as GPRs, general purpose registers. I could have stack, I could have EAX, EBX, ECX, EDX, ESI, EDI, EBP and ESP. All these things I could have. Then the scale is 1, 2, 4, 8. Index again can be any of these DS and displacement can be any 32-bit displacement. And I could have a combinations of this, okay, right. I could have just base alone, I can neglect everything else, I could have base alone, I could have displacement alone, I could have scale into index alone, I could have just index, I could have base plus scale into index, I could have scale into index plus displacement, I could have base plus displacement, all possible combinations I could have, right. And if we actually go into if the Intel manual, you will see that just to handle this complexity there is something called mod r/m plus scale index bytes, SIB bytes, and it is a big matrix that you see in 2 pages, very big matrix. So, the way this is translated into machine language, that is your base, this addressing mode is translated into machine language, that should be a representation, right. So, when the machine sees, it should know that this is a base, this I should know this is a displacement, it should know this is base plus scale into index, it should, all these combination the hardware should understand. So, you should translate it in a way that the hardware understands. So, for making the hardware understand what sort of memory addressing you are trying to do, there is something called mod rm plus SIP bytes, 2 bytes there, mod rm byte and SIP bytes. So if you look at the Intel manual 2 first or manual 1 last, you will see a very big page with this mod rm and SIP bytes. Okay. So there will be something close to 512 entries or something like that. Before going into why we need this, I should also tell you that Intel provides this to 512 bytes, right, of extensively extremely complex byte representation. The compiler actually sweats it out to create that representation. Then the hardware again sweats it out, consumes lot of your battery power to find out what you are representing. So all these are put into your hardware. Please note that this interpretation of your instruction is done by your hardware. So there is an hardware which is going to interpret your mod rm and SIP byte, right. So but when we use traditional compilers, right, some of the compilers we say I have a 32-bit version of compiler, all these fellows shouts. If you use those compilers, if you go and disassemble the code and see, out of say all this 512 possible combination, 10 combinations are only used. There are some combinations which are never used. You take all the codes, disassemble them and see in a particular domain, like you can take all your network domain or your web transaction domain or your financial transaction domain or normal computing, normal C code engineering domain. Very rarely you will see all these addressing modes completely used. You will see only 10% or 20% of this 256, rarely 10 or 15 of your 512 bytes getting used to them. So all the remaining thing are inside your hardware. They are part of your decoding, right, decoding. They consume power, they heat it up for some fan to cool it further, and again the fan will get heated up and this will cool it. So some adiabatic thermodynamic cycle is happening there, that nothing is getting used. So the point here is that when that's why many of these many of these hardware companies, processor companies do have their own software division. They will have their own compiler division, and the work of that compiler division is to see how to use this hardware. So I always say hardware is like building a dam. You have to fill it with water, otherwise there is no use for that dam. Who will fill it with water? A good compiler will fill it with water. You are understanding this, right? So when I give an interface, there should be a layer which will try and use that interface to the best possible thing. So that is why many of these companies today, if you go and look at Intel, AMD, IBM, all, they have a very, very strong software division which will write compilers and other things to basically see that that hardware is utilized very well. Okay. So that is another very important thing that we need to keep in mind. Now coming up, why at all these so many complexities that we are looking at, right? Now all this, who is driving all these things? There should be some programming language construct that is going to drive this, right? Now for example, if I have int star I, this is a pointer, right? Correct? How do I manage this? I store, so I will be say stored in some 1004. I will be stored in 1004 which has some 3000 value, right? Now when I say star I, it is the content of 3000 that I am trying to access. So this value 3000 will be stored somewhere in 1004 and I am going to access this 3000. Okay. So there is one indirection that is happening here, right. So this I will not store the address, but will not store the value, but it will store the address where it is stored. Now how do you go and manage? You manage it with basically these the instructions, the register addressing modes, right. So there are something called LEA, what you call as load effective address. Okay. So there are certain instructions that I just leave it to you to go and find out what is LEA. Now these are instructions, and then that LEA will basically try and load into a register again. So, we need something like 3000 in a register. So, some register EBX has 3000, I need this 3000 there, then I can go access this 3000. So, star I would be the content of 3000, which is nothing but the content of 1004, correct? Are you able to follow this, right? Star I is the content of I, right? Star I is the content of 3000, which is this. So, there are instructions basically used to handle these type of activities. So, LEA is one instruction which can be used, but nevertheless suppose I have, so let us just use where we are using one register for addressing memory. So, suppose I have int I, int A of 100, right, and then I say I equal to, for I equal to 1 to 100, I just do some processing on A. So, what I can do is first EBX will be storing A. Let us say A starts at 1500, okay, A of 0 is stored at 1500 plus. So, EBX will have A, right. Now, and what I do every time when I start doing here, I will increment EBX by 4 and I will access EBX. Are you getting this? I will increment EBX by 4 and I will start accessing EBX. So, what is, as my loop goes on from 1 to 100, A0 would be 1500, when I come to A1, sorry, when I come to A1, then what happens? By the time I increment EBX by 4, so it is 1504 and the content of 1504 this. So, I can basically have EBX, one of the, so EBX is basically we will use EBP also because it is a base pointer, sometimes we can use ABP, right. So, I can keep incrementing that register, I can use any of these registers, but I can keep incrementing the registers to keep accessing the next and next elements. So, this is one use of register addressing mode, register based, register direct memory addressing mode, right. If I just use this register, this is register direct, right. But then we need to go and talk about the other parts like, right. So, I said base plus scale into index plus displacement. So, how do you do this? When will I use base plus displacement? Suppose I have a struct, so I have int I, int j and something, okay. So, the structure will be stored, structure will start at 1000, I will be stored from 1000 to 1003, while j will be stored from 1004 to 1007, okay. Now, where will, so I can use say 1000 as EBX, then I can say EBX plus, when I compile, so I assume that the structure, base of the structure will be loaded at EBX. So, I can now say EBX plus 0, just EBX would be I, and EBX plus 4 will be j. So, this gives us base plus displacement. So, other thing is if I do not have something like struct, this is quite easy. So, I have main and in which I have int I j k, as I told you in yesterday's lab class, the compiler will assume it starts from 0, whenever it wants to access I it will say 0, j it will say 4, k it will say 8 and so on. So, just displacement also. So, we have seen just displacement, just base, base plus displacement. Now, let us talk about scale, index, etc. where do I use base plus scale into index plus displacement? Can you give me some interesting things? Array of structure or structure, a structure in which there is an array. Both of these are okay. Now more than that, why do I want the scale and scale into index? So let me go into some very nice thing, right? So suppose I have a loop. This loop is trying to manipulate data types of different sizes. This normally you will see, right. It will manipulate say a short integer which is of say 2 bytes. It will manipulate an int which is of say byte 4 bytes in sense. It will go and manipulate a double precision floating point which is 8 bytes. All this can happen here, right. So there could be some Ci is equal to Ai plus Bi. There could be some A, B, C, D. Ti is equal to 4 into A, B, C, D, Ei. Then I could have Fi is equal to 4.0 into Ki. All these things can be part of your, right. Then what could happen is that this I is a variable, I would like to keep it in ECX. C actually stands for a counter. So normally when the compiler translates, the C always goes for a counter. Okay, so there's also A stands for an accumulator or an, so there were initial architectures which had only the A registers, just an accumulator based architecture, right. C stands for counter. So like that SI and DI, they stand for index registers. We will see some of them in the next. SP stands for stack pointer, BP stands for base pointer, etc. So normally ECX will go, and like what we did in one of the earlier thing, let me try and go there. I don't want to keep modifying the TBP, right. Here what did I do for I just as the I got incremented, I kept adding 4 to this. But I don't want to do it because I want the ECX to represent I. If I keep modifying ECX, as I increases, if I keep modifying ECX by 4, adding 4 to ECX, then for this I should add 2 to ECX, for this I need to add 8 to ECX, right. So I have to modify ECX in 3 different ways to handle these 3 different arrays, which is going to be extremely complex for me. I don't want to do it. So what I do is, when I am doing accessing this, I will do it as 2 into ECX. When I do this, I will do it as 4 into ECX. When I do this, I will do it as 8 into ECX. And after doing one iteration, I will say increment ECX. And I will make the base of, no, there are so many bases here, okay. So we'll try, there's a lot of work that needs to be done here, okay. But this is how I will use this scale into index, right. The scale is used because I would like to maintain one counter variable, and if that loop is going to handle multiple arrays of different sizes, then I need to basically go and modify these syntaxes, right. Now ECX will be I, and I will keep incrementing ECX as I proceed in your iteration, but then accessing individual entities here we will go with the scale. So that is an use of a scale. So the notion of scale came into your this addressing mode because we wanted multiple data types. So when an array acts, when a loop acts on an array of multiple data types, then scale becomes very useful. Okay, now can we tell what base plus scale into index plus displacement? Can you give me one example, right? So I can take a struct in which I could have a string, okay. Okay, right. So how do you do this? Or int you do some 48 courses, right? So I'll put okay. So how do you so where we can use this? So there could be a base. This struct would be say student record. So there could be a base. So let's say this record is stored at 1000. The name starts or your marks actually start. More than name, marks would be interesting. Okay. We start at say some 15,015 and it's 44 bytes. And so on. Okay. So when if I want to access marks I, right, and this let us say so I say 1000 plus the displacement would be this 15. 1000 is the base. I am accessing some field which is at least 15 bytes away. So this will be 15 plus I say marks of I, right. So I is this index, that will be this index. So I want marks of 4. So 4 and int is the size of this. So 4. If I want marks of 8, marks of say let us say marks of some 13, your 13th course, then essentially I go and say suppose I start giving you real marks, okay. So double, then this will become 8 into 30, right. So we can create one example. So this is base plus scale into index plus you can construct several such examples. Now this also explains why this particular combination is very rarely used, okay. So what we have done today, we have understood about the relationship between opcode and operands. What are the benefits of a RISC architecture? What is orthogonal ISA? And then we went and discussed about different types of operands, and we also showed some mapping between C constructs and the way we address these operands. Okay, thank you.